Hello guys, we are back with another Radioshack special. So experiment segment 77, non-inverting, single power supply amplifier. Yeah, I had made a video about the same kind of amplifier, so non-inverting, but that time it was a two power supply. So I'm gonna put a link to that video right now. You may think that there's not much difference between two power supply and a single power supply, but actually there is a difference. I mean, there is a difference that's interesting to look into. So this is from the manual of that 130-in-1 electronic project lab thingy from Radioshack. And let me zoom in a little bit on this circuit. Maybe one more time. Alright, that looks good. Okay, so again, input is an earphone used as a microphone. High impedance microphone. So you have high impedance microphone, and basically it goes through a control, which is a pot for the volume. Then there is a cap, and this is an important cap. This is a voltage divider. So yeah, so the power supply, the single power supply is here. It's 9 volt, and you can see there's no tap here. So it's 9 volt. So it goes through here. Voltage divider 10K 10K. So the voltage here, if you look only at the DC, of course, is gonna be 4.5, half of 9 volts. So 4.5 volts here. So this is the plus. So that's the non-inverting input. And it's called non-inverting because then the output, which is here, is gonna be in phase with the input. So that's why it's called non-inverting. And non-inverting is always the plus. This is the inverting input. And okay, I was talking about high impedance. So you have high impedance here from the microphone, and that could potentially be a problem for the amplifier. But the amplifier has also a very high input impedance. So this one is high output impedance, this is high input impedance, because there's a huge impedance here, or resistance, between the plus and the minus input. So here there's a huge resistance here. So that's fine in terms of power transfer, so no problem. So this is your the other input. This is the inverting one. And what happens is that the output, if we just look at the DC for now, but the output is such, and even with your DC and AC, but the output is such that it's going to make sure that the voltage here at 68 is the same as in 69. So here you're going to have 4.5. And this is that whole thing here is a almost typical setup for a op-amp, but I'm gonna go back to that. So this is your feedback loop. So you have a 100K, and here you have your which I usually call RI. So this is the input on the inverting side. So you have 100 ohms, and the amplification factor is basically R1 over R2. So in this case, about 1,000. And again, you have a cap here, an important cap. Okay, that you wouldn't have in the case of a dual power supply, dual power supply. And you wouldn't have that one either in case of a dual power supply. So it's a bit different. And I'm gonna try to explain why you need those caps. And other than that, it's pretty much the same as the other. It's the same as the other ones. You go through a output transformer to match impedances, and then to the speaker. So when I actually built this thing, and I will gonna go to the bench at some point. But I was looking at the voltages, DC voltages. So basically all the voltages should be 4.5. And they are actually 4.75 because I use relatively fresh batteries. But let's look at where they are. Where did I measure? So I measured at 69, so 4.5 because of the voltage divider. I measured at 68, again 4.5. This is because of the way an op-amp works when you have a feedback loop. And 67 is also 4.5. This one is a little bit, you may wonder, how come there's no amplification of the DC voltage? I have 4.5, how come I don't get something larger? I mean, not 1,000 times 4.5 because you're limited by the plus here on the battery, which is 9, but you would expect to have more than 4.5 here at DC, but actually you have 4.5, and I'm going to explain that in a few. Okay, so the next, I'm going to go back quickly to re-explain the op-amp, the non-inverting op-amp, in case you forgot. I explained that a few times already, but it doesn't hurt to do it again. So let's do that now. Okay, so this is my famous slide about non-inverting amps. So op-amp, closed loop. Yeah, if you don't have that feedback loop, the op-amp is going to have a very large amplification factor, which is pretty useless because you're going to go into saturation right away. So here, with the feedback loop, the AV is going to be much less than 10,000, maybe 100, 200, 1,000. Something much more manageable. So this is the setup. Your op-amp proper. So the input, so this is your input. Let's say you have an AC signal. Goes into the plus, which is the non-inverting input. Non-inverting. And on the negative side, the negative input, this is the setup. So you have the Ri. And on the Radioshack circuit is that it is that 100 ohm resistor connected to ground here, and this is the feedback loop, the RF. And on the Radioshack circuit, that RF is 100K. So, and this is the output going through the load, whatever. So this is the output. So you have amplification, and you have you don't have an inversion of the you do not have inversion, so they are in phase. So that's why it's called non-inverting. And the important thing to remember is that the amplification factor, the gain, is equal to RF over RI plus 1. So usually you just don't care about the plus 1, so RF over RI, that's all you need to know. And Rin, so Rin is the input impedance, and Rin is very, very large. Because if you only look at your op-amp setup as a black box and you want to know what is its input impedance, you look like this and you see right away here you have a very large resistance or impedance. This is very large, infinite. Okay? So that's about it. Okay, so let's move on. Now I want to explain something else. And maybe it's obvious to you, but it may not be obvious to everybody. So I'm going to go through it. So this is exactly what's on that circuit. So you have the input side, capacitor, voltage divider, 9 volt. So the input goes on the plus side of the non-inverting input. This is the inverting input, and it has a capacitor, and then 100 ohm resistor, then ground. This is your feedback loop with the 100K, and this is your output. Now you may want, so here we are only talking DC, DC only. And the question is, what is V out? Do we get amplification? And again, when you have DC only. So we know that V in on the plus side, so this guy here, is 4.5 volts. So there's no denying that. And V out, as you know, when you have a feedback loop in your op-amp setup, V out is going to be whatever makes V in minus is equal to V in plus. Whatever makes V in minus equal to V in plus. So V in plus is 4.5, so V in minus has to be 4.5 as well. Now, so again, V out. What's V out? So here there's a cap. You see the cap here? So basically, when you look at the DC only, it's going to charge to 4.5, and then what's going to happen, there's going to be no current here. There's going to be no current. As you know, a cap blocks DC. So there's no, it's like you can remove the whole thing. You can remove this whole thing. And this is what I show here. All this stuff is open now. You have the 4.5 and nothing else. On the other side, on the V in minus side, again, you have a cap here. So you can get rid of all this stuff. It's like open here. So you only have the feedback loop with the 100K. Okay? So if you want to simplify even further, so you have your 4.5 volts from the minus, and then you have a huge resistance here. So it's like being open. So again, you could get rid of this if you want. You have a huge R, so up. It's like being open. So this is what you got. That's all you got. So, okay, so let's assume I didn't put 4.5 volt there. So you know you have 4.5 volts here. You have a resistor, and you want to know what V out is. Well, there's not much of an issue finding that out. It has to be 4.5. It has to be 4.5 because there's no current. So there's no voltage drop. There is no voltage drop. It has to be 4.5. Okay? Okay, so now I think it's time to go to the bench and see how it actually works. So now we're on the bench. So again, so this is where the earphone microphone should be connected, but I'm gonna connect a, I don't know if you see it, I'm gonna connect a signal generator. So it's on. Now let me turn this whole thing on. Okay. So this is the control volume. So this is on the schematics. That's what's connected directly to the earphone. But here it just controls the volume. I'm gonna keep it low. And you can control with this thing. You can control the you know, the pitch and everything, and you can control also the intensity. But I'm gonna keep it low so that not to be too annoying. Okay. So that's your signal, AC signal. And here I'm gonna show you I'm gonna show you the output. Hold on. I'm gonna show you the output. First the output. Okay, so this is the output. Of course, my trigger is not set correctly, so I'm just gonna stop it. Okay. So as you can see, it's riding on 4.5. The DC is 4. So it's offset by 4.5 volts, and you get the. So each little subdivision is actually 5 volts. Each little subdivision. So you have like 8 subdivisions, and each one is 5 volts. So you can see it's riding at 4.5. So the sine wave is riding around 4.5 volts, as expected. So let me run it. So let's look at the input just to see. So the input is 69, non-inverting. And as you can see, there's no signal, at least no detectable signal. And again, this is the DC offset that you're saying at 4.5 or 4.75. Let me see if I can display it by removing the DC coupling. So I'm just having the AC coupling, so I got rid of the DC, and I'm going to try to make it show up. So here I'm going down in at some point it should show up. Okay, so now it's showing up. So this is the input. As you can see here, I have 100 millivolts. I'm not sure what that means actually, 100 millivolts. Is it per subdivision or per little subdivision or per big subdivision? I think it's per big subdivision. So I think it's 100 millivolts for those 8 subdivisions, not for each subdivision. So that's a bit confusing. But anyway, you see the idea. So here. And here I'm going to keep the AC coupling and I'm going to go to the output. And it's a huge gain. Well, assuming I can get that clip out. It's a bit annoying. So I'm at the output now. As you can see. So now I have to go back to 200 millivolts, 500 still. Okay, so I need to go to the highest setting, 50 volts per subdivision. It's not per subdivision, I think it's per... yeah, I'm back on the computer. Yeah, I don't really know that subdivision business. I'm gonna have to, investigate that scope thing, because that doesn't make any sense. So I'll probably make a video on how to use that scope and learn something. So stay tuned for that upcoming video about that, I think it's called DSO 138 scope. I think I'm gonna have to make a video about it. Anyway, so let's go back to this schematics. So again, because you are using a one power supply instead of a 2 power supply, you definitely need this cap here, the 3 point. Definitely need this cap, the 3.3. You need this cap. You need that cap, and you also need, you need that cap, because remember the voltage, the AC amplifier signal is riding on a 4.5 volt DC signal. So you need the cap to get rid of that before going into the transformer and then speaker. Okay, so I think I'm gonna stop here, and I'll see you around. Bye.